All right, we're going to look at how to break a vector down into its components. This is either for the purposes of breaking up a kinematics quantity that needs to be in separate dimensions and kept separate, or for breaking many vectors down into their components to later add by components. So to show you how to do this, I need a practice vector, something to work on. So I'm going to draw a random vector. It doesn't really matter what it is, so I'm just going to do an auto shape here. And we'll do just a random arrow. There we go. Okay. So this is a vector. It could represent any vector quantity. Let's just give it a name so we have something to work with. How about vector E? I don't know why, just because E. Why not? Okay. Okay. So this vector is in 2 dimensions. Sometimes that's not a good thing. Sometimes we need to break our dimensions up. So I'm going to break these into X and Y components. So for this one, the X component would look something like this. So I'm going to try and freehand this. I'm using a dashed line to draw the components because in physics, actually drawing the vector means that it's a real quantity that's measurable. Whereas this component, which then I would call this like EX. So this is vector E, its X component. But it's not a quantity on its own. It's just a component of this one that is real, that is vector E. Maybe this is a velocity. Vector E is like, I don't know, 3 meters per second, kind of up and to the left. A EX, there isn't a single velocity that's just to the left, but we just talk about it, this component. So it's dashed. Sorry, I'm sick, so I'm not running on all cylinders here. The Y component would look like this. Okay, at least this is one thing. Now, to draw components, there's basically just 2 requirements, okay? It is the vector components, there are 2 vectors. There's 2 components. Those 2 vectors need to, well, they need to add up to the original vector. So in this case, E. And you can see that EX and EY, they are laid tip to tail. If I was just given EX and EY as vectors by themselves and asked what is EX plus EY, well, EX tip to tail to EY, I do in fact get E. E would be the resultant. So that works. The only other requirement is that these 2 vectors are perpendicular to each other. Okay, now technically, the ones that I have drawn is only one of many, many, many pairs of vectors that would be considered the components of E. I want to draw another one just to show you basically another one. So I'm going to copy and paste E. So it's literally E is the same here. Okay, E has not changed, but I'm going to change the components that I've made for E. So, go away. Let me do E. There's E. Okay. So, these ones I'm about to draw would also be valid components, technically. Okay, so let's see. How about, I need to scroll down a little bit to see this better. If I did this way, I have to look at it with my head like tilted over to the side to get this right. You can't see me doing this. My voice might be weird because I'm moving away from my mic to do this. Where would it be? It'd be... Oh, I can't do it sideways. Oh, I'm doing such a bad job. Okay. Woof. Okay, let me fix a couple little... When I'm at school, I just tilt my tablet. This is harder at home. I'm using a Wacom tablet. There we go. Okay. Boy, all right. And then put directions on these things. Anyway, I can't tilt it the same way that I can with my physical tablet. Okay. Oh gosh. Okay, so that's supposed to be a right angle down here. Right there. That should be a right angle. It's okay. It's not a great one, but Technically, the red and the green on this second one are also components of E, like it's a different set, because they still add up to E and they are perpendicular to each other. That's all that matters. Please note that whenever you break a vector into its components, you will end up with a right triangle with E as the hypotenuse. That's what's really important about these. For this first unit, we're only going to be using basically the ones on the left, but it will be useful later to tip our X and Y axes to more match like the one on the right. So that is a thing that you will be doing at some point. But for now, let's look at the other one that looks a little bit simpler. Got a nice right angle there. So it's often very useful to break your vector into its components, and it's conveniently a right triangle. So to break up the right triangle into its components, we just need to know this angle here. We need to know an angle somewhere in the triangle. So when you're asked to make the components of something, draw a triangle. Draw this triangle, identify the angle that you know, because they'll give you something. They will give you an angle. And then you're going to use it with right triangle trigonometry to figure out the magnitudes of EX and EY, at which point you will put on if they're negative or positive. So like in my little drawing, if I made, say, I'm going to do this. If I decide that up is positive and down is negative, and if I decide that right is positive and left is negative, technically EX is a negative number, but we'll get to that. Okay, so let's do some right triangle trig. This is probably review for most of you. I'm looking at this triangle, and let's say I want to know what EX is. Well, I've got an angle. That angle is adjacent. It is touching EX. So I'm probably going to use a trig function that uses the adjacent side. I know what E is. I will have been given it. So I also want to use the hypotenuse. The one that comes to mind is cosine. I know that the cosine of an angle equals the adjacent side divided by the hypotenuse side. In this case, the adjacent side has a magnitude of EX. Note that I have not put the vector sign over the EX this time because only magnitudes go into this cosine and this one to this cosine. You can put a negative in there, but it's not really going to help you per se. And same thing with E. I'm putting the magnitude of E. I could then rearrange this and find out that EX is equal to E cosine theta. Okay. It won't always be EX is the cosine. It really depends on your triangle. You need to make this make a triangle from scratch every time and then apply a sine and a cosine to it. So if I do a sine, I get that's opposite side. So across the triangle from the theta, and then hypotenuse, in this case that is EY over E, which means the magnitude of the Y component of E is E sine theta. Okay. Now again, I'm only doing magnitude here. You will need to put in any negatives or positives that are necessary. For example, I decided that left was negative and EX is to the left. So technically, I should be putting negative E cosine theta for EX, for EX, because I decided, I decided that left was negative. So I have to add the negative is. Okay, I have to put the negative in, the negative in. Yeah, okay. If you decided left was positive, then I would have left as a positive. Excuse me. Okay. Most of the time, you will be breaking up vectors into their components like this. Either just that's your end result or it's on the way to a larger problem. Sometimes you will be asked to put them back together though. So if you look at this triangle and think, oh, I know what EY and EX are. What is E? What is theta? We're going backwards. that is where you get to use your nice Pythagorean theorem. I love the Pythagorean theorem, so nice. Okay, so if I had EX and EY, I know that the hypotenuse magnitude squared is equal to the legs magnitudes squared, which means I could find the magnitude of the total vector by doing this. You'll be doing this a lot, although not as often as you'd think. We do the breaking up a lot, but not a ton of the putting back together. I'm having trouble with E's. EY squared. Okay. If you need to know the angle for any reason, it's a little bit rarer to ask you, but if you need to find it, you're going to have to do an inverse trig function. So you could do the cosine, like cosine equals EX over E, and then take the inverse cosine of both. You could do that with sine and the EY, but most people tend to use the tangent. So tangent is opposite over adjacent. And we tend to use this one because we are often, if we're asked to find this angle, we're usually being given the X and Y components. So in this case, in this triangle, I would look at my triangle, make the triangle first, look at the triangle, and say, okay, my opposite side, that's EY over EX. And then I take the inverse tangent of both sides. When you take the inverse tangent of a tangent, it just leaves theta behind. It's kind of like taking the square root of a square. Like that just leaves, it undoes the square root and the square. And then on the other side, I'm left with the inverse tangent of EY over EX. You have to be careful with this though. This is only going to give you the angle with the x-axis. You have to decide exactly what that means. Only gives angle with x-axis. So for instance, if I had numbers about this little triangle over here, it would, what does that look like? Looks like about, 35 or 40 degrees is what would pop out. Okay. You have to decide if that's like which quadrant that's in, basically. Okay. Like if this returned to you like 35 degrees, you have to decide if that is here or here or here or here. Like you decide which one it is, and you have to somehow describe which one it is. So like, I don't know, I'm just going to give these letters so I can talk about them easily. Like A, I might describe as 35 degrees above the negative x-axis. Okay. B, I might describe as 35 degrees above the positive x-axis. C is 35 degrees below the negative x-axis. You also might be able to use words. D, I might describe as 35 degrees below the horizontal or below positive horizontal. I've even seen kids say things like C is 35 degrees below left. I mean, that's fine. Below left is fine. Okay. Anyway, this is enough for this notes. This is all about components. So this is components. Components make right-angled triangles.